In this video, we're going to learn about elastic collisions. This is going to be a collision where all of the kinetic energy is conserved. Now, normally all energy, the total energy is conserved, but in other collisions, some of that kinetic energy could transfer to other types. Maybe we'll have some kinetic energy. Some of that kinetic energy could go to thermal energy. Maybe some of it would go to deformation. Like these balls hitting each other and maybe one of them breaks. Maybe it gets a big crack in it. That would be a deformation. It would lose some of its kinetic energy to do that. Or maybe some of it makes sound. Like if you've ever heard a car crash, there's a lot of sound. Well, that sound is kinetic energy being moved around into other types of energy. So what we're saying in an elastic collision is that none of this happens. A perfectly elastic collision, all of that kinetic energy stays as kinetic energy. It doesn't transfer to other forms. And so with that in mind, we're going to be able to solve these. Because first off, we still have the conservation of momentum. The conservation of momentum states that the initial momentum will be equal to the final momentum of this system. What is our system? Well, our system is going to be everything within these two lines. It's going to be both of these balls rolling at each other. And so we could really say these two balls have a nice center of mass. That center of mass would be somewhere between them. The total momentum of that center of mass is going to remain constant. So if I can figure out my initial momentum, then I can figure out my final momentum. I will know those two things. However, just looking at this equation, I'm going to have two unknowns. I'm going to have to figure out both of the final velocities. And that's not going to be possible with just this one equation. I need to use the fact that the kinetic energy is also being conserved. Now here I've got a second equation. This equation would also be true. Since both of these equations would be true, what I could do is, in order to solve this problem, I could put in all of my variables and let's say solve this equation for the red velocity and then substitute that in for the red velocity down here and solve it backwards, finding the value of the blue, plugging that back in to solve for the value of the red. I could get both of them that way. However, just looking at this kinetic energy equation, personally, it's a little daunting. It's a lot of work, and even though I enjoy doing mathematics, even though I enjoy rearranging equations like this, I don't want to do this for every problem. It'd be fun to do it once, but not for every problem. So let's derive a shortcut. And when I say derive a shortcut, what I really mean is let's find a shortcut. Because I can do everything I just stated and plug all of these values in up here and rearrange this equation to get a custom third equation. Because my masses are all going to be the same, I'm only going to have two different masses, all of my masses would end up canceling out. I would be able to get rid of them. And if I simplified that equation using some vigorous mathematics, I would get a new equation that would look like this. This custom equation is only true This equation is only true if the kinetic energy and the momentum are both conserved. So you'll want to commit this to memory because this, in case you haven't noticed, is not on our AP equation sheet. This is a self-derived shortcut. So we want to be able to use this. We're going to have to remember it. So let's practice. Let's use these two equations to solve this problem up here. I've rewritten my equation for the conservation of momentum. That's what this is describing because the objects won't stick together. If they stuck together, it would be an inelastic collision. But with this equation, I can plug in all of my numbers, everything I've already got. Let's do that and then simplify it. So when I put all of these together, I get 5, value of 5. So let's go ahead and use the other equation to get something I can substitute in. So now this is a pretty simple equation to rearrange. Let's solve it for the red velocity so that I can substitute that in right here. So what that's going to look like is adding that -7 to both sides. So plus 7 plus 7. 7 plus 4 is going to give me 11. So what I've done here is I've made a custom equation that I can substitute in, and I can put that in for my red velocity. So let's go ahead and do that and see how we can simplify things. So now that I've done that, I can distribute this 5 across this parentheses. So let's do that as well. Now that I've distributed that, I get 5 equals 10 blue V plus 55 plus 5 blue V. So I can put all these together. So I can subtract that 55 from both sides to get rid of it. Oh, that's not a 5. And then I'm going to add these two V terms together. And when I do that, I'll end up with 50 being equal to 15V, negative 50. Negative 50 equal to 15V. I'm going to divide both sides by 15. And my V will be equal to negative 3.3. And now I can simply plug this in to this equation right here. So I can take that and when I do that, I get a positive 7.67 for my red V, for my red velocity. So my final velocities will be 7.67 for the red ball. That would be this one. That would be a positive, so it's going to be moving this way. And then a negative 3.3 for the blue ball. And that'll be negative, so it's moving this way. So they bounce off of each other and go in the opposite directions. Their velocity is changing. In fact, the red ball ends up getting a higher velocity than it had initially. So that's how we solve these types of problems. Let's try this situation where I have both balls going in the same direction. Now, obviously, my blue ball has to be going faster, otherwise it would not catch the red ball. If you tried to set up a situation where your red ball is moving this way, but moving faster, you might end up getting some pretty funky numbers because the math wouldn't check out. These wouldn't ever collide. But because the blue ball is going faster, it's going to hit the red ball. So what's going to happen afterwards? What's going to happen after that collision? This is really an overtake problem that results in a collision. Remember overtake from kinematics? So we could take all of our numbers and plug them into our two equations, our conservation of momentum and our modified conservation of kinetic energy. Let's set up those two equations. And now let's plug in all of our numbers to these two equations and start to simplify them. Now I've got some numbers, so I'm going to simplify everything on the left side of this equation. And then I'm going to move my 5 to the other side. I want to try and keep everything as positive as I can. Notice I don't have any negatives in either of these terms. My balls are both going in a positive direction, so they're both going the same way, so I don't need any negative terms. So I'm going to try and keep that theme going by subtracting 5 from both sides so that I can keep my numbers positive. So in just a few short steps, I've simplified these two equations to just have two terms apiece and I can substitute these in for each other. And so now I've got 169 equals 12 blue V plus 5 times 7 plus blue V. So let's distribute this 5, and then let's simplify our equation. Then I'm going to subtract 35 from both sides, and I'm going to add my two V terms together. Then the last thing to do is to divide by 17. And I end up with my solution for my blue velocity. I get a positive 7.9 meters per second. Now let's plug that 7.9 in right here. And when I add 7 and 7.9, I get 14.9. Positive 14.9 meters per second, and that is my solution for my red velocity. So we can see that if we can just set these up and get our base ideas correct, then we can very easily solve for our final velocities, even though we have two unknown variables, as long as we can keep in mind that we have two equations that are both true.